Part 3 video, Chapter 9, Section 3. We did a couple of these crazy looking graphs already. I'd like to point out to you, last video we did, please ignore the phone in the background. We did this graph that has two loop-de-loops. We did a graph over here that had three loop-de-loops. And let's see what interesting things are going to happen with this guy. Folks, you gotta remember to factor whenever humanly possible. This guy factors. The top. If you see the x squared, you should know there's a pretty good chance that it's going to factor. So x squared, x and x, 8, 4, and 2. I want a negative 8. I need 1 plus and 1 minus. Check that outside, inside. That will give you that plus 2 in the middle, ready to go. Okay, you must establish what x cannot equal. Those are called restrictions, excluded values, or undefined values. X cannot equal negative 4. If I plug negative 4 in, I get 0 on the bottom. 0 on the bottom is a no-no. So if you watch the first video, there was actually a graph that was shown that ends up being a straight line. And there's obviously such a thing as asymptotes, which we talked about in the last video, but there also was such a thing called a hole in a graph, literally, which if you check out the first video, you can learn about. Well, mathematically, go back up to this problem that's now been factored. There's no reason I can't cross out common factors. X plus 4 and x plus 4 would cancel. And now I'm left with x minus 2. But the unique thing about x minus 2 is there's no more fraction. So the function, or f of x or y, is now equal to x minus 2. Do you guys recall a little thing called y equals mx plus b form, which was for linear graphs? Well, if we got ourselves a linear graph, that means I have a y-intercept of negative 2, and I have a slope of 1. So I would simply just count my slope 1 over 1 and draw that thing in. Let's see if I can actually get a straight line here. I'm so proud of myself. Simple things, guys, simple things. Arrows on the end to make it official. So you might be saying to yourself, wait a minute, what the heck's the whole deal about the whole blah, blah, blah? Well, this is why I wrote it down. X cannot equal negative 4. So if I were to try to graph that guy, negative 4, your calculator would say it's an error. So it's ungraphable. So there's such a thing as an asymptote, which is in the previous video, that shows an area that can't be graphed. If you end up with a straight line like we did here, the way you show it is a hole. So I have to find negative 4, comma, wherever that is. So here's negative 1, here's negative 2, here's negative 3, here's negative 4. So down here at negative 4 comma something, and my line's off by a little bit. Sorry, it really should have gone through that little corner right there. I have to show an open circle or a hole, because that particular spot, negative 4 comma something, doesn't exist. So it ends up being fairly easy to graph because all you're doing is y equals mx plus b form, but you have to remember to go back and stick that hole in there. All right, unique. So sometimes they can end up with the curvy lines and asymptotes. Sometimes they end up with a straight line and a hole. But either way, it represents a rational or fraction function. All right, just to recap, something that you would see on a quiz. Let me scale this back down so we can see it. So some graphs have asymptotes, some graphs have holes. Let's recap for you how you find that. So if I look at number 14, I see that x cannot equal 0, because I literally can't put a 0 right there. I would have 0 on the bottom. Two numbers in that set of parentheses, so here's that trick again. X cannot equal 1/4. And that would be for that particular x. But there's nothing common on the top and nothing common on the bottom to cancel out. And if there's nothing to cancel out, there are no holes. The parts that cancel out make holes. The guys that don't cancel out are asymptotes. So there would be a vertical dash line at 0 in that drawing and 1 at 1/4. Not going to make the drawings. I'm just going to talk about holes and asymptotes just to refresh your memory. Second problem, when in doubt, factor it out. It's kind of tough for me to tell if I can cancel the x plus 2 on the top with something on the bottom if I don't know what's on the bottom. Not coincidentally, 7 times 2 gets you that 14. Nothing but plus signs. So let's establish what x can't equal. X cannot equal -2, because if I plug that in, I would get 0. X cannot equal -7, because if I plug in -7, I would get 0. But which one cancels? That x plus 2 and that x plus 2 would cancel. And anything that cancels would have made a hole in the graph, like the graph we just did a couple minutes ago. So there would be a hole at x equals -2 or -2 comma something. You would draw a hole there. Well, which one's not crossed off? That's the -7. And that would make the asymptote. Can I make you tattoo this on the back of your hand? Apparently not. But better remember it. If I do a GCF, I've got that. Bottom only is where the restrictions occur. I cannot have -4 for x, otherwise I get 0 on the bottom. So the question is, does it cancel or not? Well, this guy is a binomial. This guy is a monomial. You can't cancel them. I can cancel a binomial with a binomial like we did back here in number 15. I can cancel a monomial with a monomial, but I can't cancel those two guys. So if nothing cancels, there are no holes. The thing that's left on the bottom that's uncanceled was that -4. So he would make a vertical dash line in the graph. All right, so hopefully that's not too bad. Now, I understand making the graphs can be painful. So we're going to take a look at one more. I scribbled out the one that was there. I'm going to give you a new one here. I have no idea why the fraction bar is that color, but I don't know how to change it. So I'm going to cut to the chase here, guys, and I'm going to say, just based on the graph, I could cancel the x plus 4s, which means my value of -4 would have to be a hole. And there would be the x minus 3 left on the bottom. Restriction is x can't equal 3. That would make an asymptote. Well, if the asymptote's x equals 3, and check out a previous video if you need to, that makes a vertical dash line. Now the actual graphing process would be to pick points, some x and y's, and plug them in and figure out some numbers. And don't forget about plugging in a big number, -100 or +100. And if you do plug in those numbers, it ends up being really, really close to 0 and really, really close to 0. So I would have a horizontal asymptote. Hopefully you guys can see this. Your teacher being partially colorblind, I really can't see it all. I'm just going to assume it's there and hope you guys can see it. All right, now I'm not going to bother plugging in a bunch of points because I'm not going to have time. So that's how we do get the graph, but I'm going to tell you this section would end up down here. And he would be really, really close to 0 but not go through, and really, really close to +3 not go through. And the other portion of the graph is up here in the right corner. And he's really, really close to +3 and gets really, really close to 0 and doesn't go through. But the reason I'm bothering to do this is to show you it is possible to have the loop-de-loops. It is possible just to have a straight line, but it's also possible to have the loop-de-loops and a hole in the graph. So this is what we did on that last graph, and this is what you would have to do on this one. So you would have to find the area where -4 is. So -4 comma something. Well, -4 comma something, well, that wasn't supposed to erase that whole thing, but that's okay. We'll just do this. So -4 comma something, 1, 2, 3, 4, would be right there. So if you can imagine that's a hole, because that was really hard for me to make, and I'll reconnect the graph. So not only do you get the loop-de-loops on this one, but you get the hole as well. All right, that is the end of Chapter 9, Section 3. Thank you for watching. Hope you followed.